Okay, I'm sitting here with Dr. Falk Mersman, and we're gonna talk tendons. So tell everyone who you are.
Yeah, hey Jake. I'm Falk. Yeah, as you said, I am located in Berlin, in Germany, and I'm head of a small research group that is interested in the adaptation of muscles and tendon to mechanical loading under the supervision of Professor Adamantios Arampatsis. Uh, and he has been interested in the muscle tendon function, yeah, I think more than 20 years now, and developed a lot of methods that can use to approach these questions in living humans. Yeah, that's what I do.
So how did you get interested in tendons? Did you have issues yourself, or how did this come about?
Yes. Well, basically, it was just a coincidence. I've been working as a student assistant in this department here already when Professor Arampatsis came, and he brought this topic with him. So I was not too much interested or didn't know anything about tendons so much, not more than any other sports scientist. But I'm a volleyball player. So of course, I personally I was not affected, but a lot of my teammates and yeah, it's a big issue there. So I was very happy that yeah, this coincidence was able to I don't know connect some personal experiences uh, and basically also a cohort which is largely affected with my new profession. Yeah.
So how many years has it been since you've been doing this type of research?
Sorry
How
again.
many years has it been?
Yeah. So I started my PhD, which was on muscle and tendon adaptation in adolescent athletes. I started in 2011, and I finished in 2016. And since then, yeah, I'm working as the head of this research group, and there have been several PhDs also under my supervision afterwards. And we basically, on one side, tried to uh, look more closely into the fundamentals of tendon adaptation in people. And the more applied side, let's say, to try to use this knowledge to prevent tendon overuse injury in athlete populations at risk, and also to treat patients with tendinopathy.
So this initially came, I guess we're kind of getting into your Berlin method, but did this start in adolescence?
No, this Berlin method basically uh, this this was derived from the fundamental research that was started initially in Cologne by Professor Aron. And he made thoughts how to systematically investigate the factors that can affect tendon adaptation from a tendon-biological perspective, which are the magnitude of tendon strain. So basically, all of tendon adaptation is strain mediated. That is the most important mechanical factor. So the magnitude of tendon strain, the rate of tendon strain, so how fast the tendon is stretched, the duration, how long the tendon stretch is kept in one loading cycle, and the frequency. So how many times in a given amount of time is the loading cycle repeated? And he started addressing these questions in around 2004, 2005. So first publication in a series of publications was in 2007. So before my time, actually. We in 2014, when he already was in Berlin, I was involved in continuing this research. Basically up till now. So quite recently, we investigated the effects of overall loading volume and the number of loading sessions per week on tendon adaptation. And in the future, we will look more into the role of metabolic stress on tendon adaptation.
That's what I was gonna ask. I recently talked to Gerard McMahon. He has the no strain, no gain paper. and he was talking about all of the changes in stiffness, probably cross-sectional area being strain mediated. What have you? Where do you stand with that? There's a strain mediated idea, but are there also these metabolic factors that can lead to changes in stiffness and cross-sectional area? Have you made any progress on that, or is it too soon to say?
Well, there has been an interesting study where actually Aaron Patzes was also involved, but we didn't do it here in Berlin. And there were two loading protocols with a similar degree of muscle activation, but two different joint angle positions. One with a very short muscle length where the force capacity is low, which means that even though the muscle is activated to a high extent, the actual forces on the tendon and the tendon strain is also rather low. And the second protocol where the length of the fascicles, in this case triceps was greater, and at a given degree of muscle activation, the forces are then quite high. Also, the strain on the tendon is rather high, and it was basically confirmed that here only the high strain magnitude led to a change in tendon stiffness, even though the muscle activation and metabolic stress in both conditions was more or less simple. So that already hints or makes us believe that metabolic factors, they may play a role, of course, at a given if you have a given amount of mechanical loading, but it's in comparison to mechanical loading, way not as important. So it's a minor factor, minor factor.
Yeah. When you said all these ideas was the strain mediated. I guess before I get into that, the volume piece. What have you been looking into the volume? What is the right amount of volume that, or how much volume do people need? Is high volume better for tendon adaptation, or is low volume? I know you guys, your work is like the Berlin method takes just a few minutes per week, and you're getting big changes in stiffness. Is there comparable stiffness at a higher volume type of interventions?
Yeah, that it was a surprising finding actually. So in our latest experimental study, all groups that they did the same training, and the training consisted in every set of 4 repetitions with 3 seconds contraction, 3 seconds relaxation at 90% of the isometric AUC. And the different subgroups performed a different number of overall number of sets per week, and the distribution was also unequal. So some trained 2 to 3 times per week, and others 5 times per week. So that was also the right. And in terms of the overall volume, we found that actually only 15 sets of these 4 repetitions per week, irrespective if it was 3 seconds with 5 sets or 5 sessions with 3 sets, basically the results were rather similar, and just increasing the overall volume to 20 or 25 sets per week didn't increase the outcomes. Actually, in the protocols with the highest overall local volume, there was still a positive adaptation, so a clear increase in stiffness, but with regard to the effect sizes, compared to the low overall loading volume, the effect sizes were actually smaller. So this is very carefully suggests that basically when the stimulus for the tendon is more or less saturated in terms of the overall volume of mechanical loading, which is necessary to stimulate the tendon metabolism, that basically additional mechanical loading may just lead to, let's say, more wear of the tissue and increase the catabolic side of the response. So any loading increases both anabolic and catabolic responses. But if the anabolic responses start to level off at a certain point, then just adding mechanical loading may, in the end, either reduce the effectiveness, or let's think about really elite athletes which train 11 times a week or something like that. It may be actually too much for the capacity of the tendon to repair these to repair the micro damage that is associated with mechanical loading.
Mm. And you're thinking, so you compare these elite athletes training 11 times a week, and if they're doing like a track and field athlete who's doing a bunch of dynamic loading, do you look at that type of loading the same as like the Berlin method, the heavy isometrics? Do they both have the same ability to lead to a catabolic response?
Well, that's a difficult question. So in our experience, plyometric type of loading, the magnitude of strain is quite high, but the duration is very low, and it's also a very high strain rate. And there are some very interesting observations from in vitro studies that the ratio of tendon cells, which are actually stimulated due to a loading cycle, reduces with high strain rates. So in our view, for a physiological stimulus for the tendon, high loading is good, but at rather lower strain rates and longer strain durations. So with that in mind, I personally think it's a difference if you apply a given weekly loading volume primarily in terms of, for example, biometrics, or like we suggest with the Berlin method, which is basically not saying you need to do isometrics. It's basically saying what are the mechanical factors that are important for tendons, and the long strain durations and low strain rate seem to be something that, for example, with heavy slow resistance training, for example, we assume that the stimulus for tendons is actually quite good. Nevertheless, you can also do too much. If the anabolic response of the tendon is saturated, with additional volume, you at least increase the risk that the outcomes less favorable. Now, of course, not every elite athlete gets overuse injury, so there is even more to that we do not understand. So there's an individual factor coming into play, but there it gets more complicated.
Yeah. So you say this work, I don't know, on this tendon cells, the stimulus reduces with the high strain rates. The little bit I've seen was actually I think it was your paper with Aaron Patsis on, I believe it was called How to Train Human Tendons or something like this. It took me a long time to find it. And you guys were, the little bit you had on tendon cell mechanotransduction was that the 3 second holds you guys saw a gain in stiffness. And then the 1 second, you didn't see as much gain in stiffness, or maybe not. And so that there was this speculation you guys had that they need at least 3 seconds. It seems they need at least 3 seconds to get mechanotransduction. Is there any more pieces of research on this, that the tendon cells need some time under tension so that they can start to, whatever they do, kick out collagen or cross-link the collagen, whatever it is? Are there other pieces of research on this, or is it kind of just based off the speculation that the 3 seconds saw the gain and the 1 second didn't?
Well, actually, not too much. So that there is, I would say, in terms of in vivo human tendon adaptation, there are not many groups that do systematic research over such long time that systematically modulate specific loading variables to investigate outcomes. There are other groups interested more or they use more in vitro methods, for example. And if they do mechanical testing, they usually have this sinusoidal loading cycles, where and they, for example, this question of loading duration. I never saw a loading protocol performed in vitro where they had actually a certain time with constant magnitude of strain. It's more, like this sinusoidal cycle. But to try to answer your question more shortly, so there is not much on that, but what is there basically still supports this view. So as I've been mentioning, there's very good, very interesting research on tendon cells that demonstrate this. It's not about duration, but the high strain rate. And if we look into the practical field, that basically is usually if you have a high strain rate, you usually also have a short loading duration in terms of sprinting, jumping, change of direction, movement, something like that. So this usually comes in combination. And we see, as I said, that many tendon cells are not receiving the stimulus because maybe the distribution of strain within the tendon tissue is not as homogeneous as when the strain is applied more slowly. There are also some experiments from specimen that investigated the failure mechanisms if you increase or if you strain a tendon until failure, that the effect of strain rate is leads to a similar view that at very high strain rates you cause more localized failure, and at very low strain rates you cause more global or more distributed indications of failure, which if we go at a physiological level suggests the idea that the strain distribution is more homogeneous if the strain is applied rather slowly. And then we have the findings from different types of loadings, like, for example, isometrics or heavy slow resistance training, where we relatively consistently see increases in stiffness when the load magnitude is high enough. And then we have this studies on plyometric loading. There, the responses are very inhomogeneous. And that was also basically our results. The average increase or the average change in stiffness in response to plyometric loading was actually not too bad in our study, but it was very inhomogeneous. So it's really hard to predict how how a tendon responds to this high strain rates.
Do you have any speculation why it was so inhomogeneous? With why were some people getting stiffness from plyometrics and some were not? Were there a variety of different? Was there any commonality between those two groups of people, or was it just completely random?
Basically, I think with the methods that we are able to apply in vivo, we are very limited to identify these factors. So I'm quite sure that there is a genetic component which is also involved in how the mechanical load is converted into a cellular signal. There is research showing that there are some genes that determine how these mechanosensors in tendons work, but we have no possibility to control for that in our labs. And also, aside from that, we of course documented habitual physical activity, the sports background, and so on of the participants who took part in our experiment, but we were not able to establish clear. If you give to on first view quite similar or homogeneous population, apply your medicine in terms of our tendon training, and still the response is rather inhomogeneous. So for most, I would say we are still wandering in the dark. What?
Yeah. This I think because I talked to Gerard McMahon recently, and he in his no strain no gain paper, he had a graph, two types of people. One was a very stiff tendon, and in order for them to get a stiffer tendon, they would have to train at a 90% MVC to get it stiffer. But someone who had a really compliant tendon, they could train with really not as heavy means or not as specific means and still gain stiffness in their tendon. Do you think you see any of this with someone coming in with a stiffer tendon versus the more compliant tendon? Does that exist with all these people you've looked at?
Well, yeah, absolutely. That is, thank you for that question, because that is actually maybe not the only one, but very a key factor that we are able to control, and we started to control for that quite recently, that this prescription of loading, that we say we want to use rather high loads, 80%, 90% of an isometric MVC, for example, or 90% of a repetition maximum. That is actually, as you said, for a person who already has more or less an imbalance of muscle strength and tendon stiffness, so a deficit in tendon stiffness, this loading would actually lead to very high strains, higher than necessary to provide a good stimulus for tendon adaptation, and also maybe putting in a predisposition to develop overuse injury. So that is something that we actually can do. It's not easy, it's not trivial to determine tendon strain in vivo, but it's possible. And we just finished 3 longitudinal intervention studies where we did exactly that. So the athletes came to our lab, we investigated muscle strength, investigated tendon stiffness, and then identified, is there more or less balanced muscle tendon unit. These participants trained at high intensities, which are known to stimulate muscle strength, and in these cases also leads to tendon strain in the order of 5 to 6%, which is very good to promote tendon adaptation. Then we had some athletes which had a deficit in muscle strength. This is rather rare, but it exists. That means that tendon strain during maximum contraction is actually not too high, and since the compliance and elasticity of tendons is actually also helping us to perform well, it's a good thing for physical performance. There we said we try to find a mode of loading that is known to increase muscle mass and strength, but not so much provides stimulus for tendon adaptation. And so we chose medium loading, dynamic training until muscular fatigue. Yeah. So this metabolic stress, as we start to begin to understand, is not really a good driver for tendon adaptation. And in these individuals at moderate loads, the strain of the tendon was also not too high. So what we actually achieved with this few individuals is that muscle strength increased more than tendon stiffness. So we're restoring the balance. And the last subset of people, which is actually quite a substantial amount, so between, depending on the cohorts, 25 to maybe 40% of the athletes who have a deficit in tendon stiffness. And that means they do not need to train at very high levels of muscle force generation, but quite individually between, let's say, 50 and 75% of their NBC. And since the overall loading volume that we subscribe is rather low, the muscle adaptation is not promoted to a great extent, but more tendon stiffness. So basically also there we were able to restore a more balanced adaptation of muscle and tendon. And the benefits for the performance and for the reduction of tendon overuse injury, this is something that we need to gather more data, because pain, for example, tendon overuse, since there are so many factors and also individual factors, we actually need some larger sample sizes to statistically be able to show that this personalized approach is actually worth the additional effort, because the additional effort is actually it's a lot, but still we believe it's good, particularly for patients with tendinopathy. This is what we are currently doing in this very weeks. We're extensively in the lab and preparing to recruit participants with tendinopathy to apply this personalized approach.
Okay, I have a lot of questions on that, so I might. But I wanted to go back to, yeah, I have a few on that. I'll come back to those. But you on the homogeneous strain, when you have a low strain rate versus the high strain rate, it's inhomogeneous. It makes me think of, I did a show with Hazel Screen, and she has all that work on the interfascicular matrix. Is this more of like a viscosity component, you think? Why things can kind of shuffle around, and then you can get load in certain areas that are not going to be loaded when you're doing something that's a high strain rate? Is that what you think is happening? Is things can kind of shuffle around and you can get load sharing in all the different regions? Or what do you think is happening? Okay.
Exactly. I mean, that is also not our field of research, right? Or it's our field of research, but not our expertise here. We are looking at only global tendon strain in vivo. And for example, the group of Hazelspiel, they are very, very excellent work looking more into what actually happens within the tendon tissue. And exactly that's, so on the global level, these viscoelastic properties of tendons do not really show to a great extent, so almost non-existent. But we believe that within the tendon, these viscoelastic properties actually greatly affect, for example, how tenocytes are stimulated, how single fascicles are mechanically loaded, and also, the loading gradients within the tissue may be very much affected by this by the extracellular matrix of the tendon and the load transduction between fibrils and fibers and fascicles.
So you can't see the viscoelasticity if you look at the whole thing, because all it does is it strains or it doesn't strain, right?
Yes, at physiological loading rates, for example, we see that there is a preconditioning. So a totally unloaded tendon, if you start to warm up, for example, there you will see over about 5 to 10 loading cycles, you will actually see a change in the mechanical behavior. But after that, we do not see it anymore. And what is done in cadaveric studies, you usually have this this phenomenon that with a given load, tendon strain rather quickly increases. Then there is a plateau coming for a lot of loading cycles, and then when there is material fatigue, the strain at a given force again increases until the tendon ruptures, for example. And this is what we do not see in vivo, because usually the muscle would fatigue prior to the actual failure of the tendon. At least if we talk about acute loading, right? Of course, there is something like tendon rupture, no doubt about that, but that doesn't develop within one loading session, right? This is a development that is progressing prior to that instant.
Yeah, so I've thought that you guys have the 3-second isometrics, and when I first got into them, they were 30 seconds, like the Keith Barr prescription of 30 seconds, and I think his idea was tendon creep, that you start holding and it gets longer and longer over the set. But I've always been like, isn't the muscle fatiguing first, so it can't keep pulling as hard on the tendon, so how could it creep? Do you think something like that is similar, or do you actually get this slow elongation of the tendon even if the muscle is fatiguing?
Yeah. So my supervisor did some experiments in 2006, 2007 addressing that issue, and they both with dynamic loading and so dynamic cyclic loading and constant isometric loading. They were not able to show basically this creep effect in tendons. So initially, this preconditioning effect, this is actually observable, but basically then indications for failure, let's say, we do not see it in vivo. We don't, no.
Uh-huh.
But yeah, nevertheless, basically what the ideas we are sharing with, for example, Keith Barr here is that there is stress relaxation within the tendon. We believe it's not an important phenomenon on global tendon strain that really has an effect on, for example, performance or something like that. So that the deformation, the compliance of the tendon is really substantially changes so much during competition that it actually affects performance so much. But yeah, that where was I going now? Yeah, that within the tendon there are these effects that determine how strain is distributed to tendon cells, and that this is one factor why we also promote slow types of loading with longer contraction durations. But yeah, we have a longitudinal study where we applied single contractions of 12-second duration, and we found that we were surprised that 5 sets with only 1 repetition over 12 seconds is actually increasing tendon stiffness. That was a big surprise for us, but still doing not 1 cycle of 12 seconds, but 4 cycles of 3 seconds was the more effective approach. And we don't know if 6 seconds may be better than 3. We are not able to change our protocols so slightly. Now we look for the contrast there. And of course, we are not talking about you mentioned 1 second in another study. We had 1 second loading, and there was actually some changes in the tendon, but 3 seconds was more effective. And there's not the fixed threshold that you need to go over, but it's more a range. And the, let's say, multi-second range, that does probably a very good trick. And after a certain time under strain, probably you do not benefit that much, and it's better to release and to contract again. So from my point of view, the 30 seconds contractions in terms of changing tendon mechanical properties, it's unnecessarily low. I would reduce it. But you also, one thing, the things are unfortunately, or maybe for scientists, it's also a good thing that they are complicated and that there are many facets to it. I'm only talking about changes in mechanical properties. If, let's say, a physiotherapist tells you, and there is this work by Ebony Rio, probably already know that they were focusing this pain aspect, and why we say the contraction type, isometric, concentric, eccentric, the tendon has no sensors that, translate this. And there is, I think, to date, exclusively evidence supporting the idea that force and strain, or strain is the dominant factor and not the contraction type. But in terms of pain release, there's at least some work suggesting that isometric have kind of a special effect. It could be, on the sensory aspect, this could be a different story. But from the focusing on the tendon mechanical properties, I would argue that the type of loading, the contraction type doesn't matter too much, and it's better to use a little bit more loading cycles than extensively long contraction durations.
This makes me think of, so when there is the tendinopathy, because you guys have some work in tendinopathy, right? In younger kids with tendinopathy, patellar tendinopathy. But it makes me think of, you were talking about this I think it was 4.5 to 6.5 strain was kind of the area you want to get signaling. But then our kind of discussion on the individualization, like some tendons are stiffer, some are more compliant. And I'm thinking of the tendinopathy case. And to me, it seems like those tendons are more compliant. Like they've shown it in the Achilles and the patellar. they did shear wave elastography and they didn't. So it wasn't really a good comparison because they should have probably done ultrasound or something. But I'm thinking it's so easy to set off those tendinopathic tendons with like a 3-second super heavy isometric is probably more likely to set off a pain cascade versus maybe a lighter 30-second one. I don't know if this is anything you've speculated on of people with tendinopathy. Is this why you think they might respond better to longer duration, lower load, or do you think it's something else? I'm looking at it and I'm just thinking it has to just be less strain on the tendon, so it's probably just better for the tendon if it's really sensitive.
So you certainly, with regard to this personalization aspect, tendinopathy is or patients with tendinopathy are an extremely interesting cohort because, as we said, it's not consistent finding that the mechanical properties are so the stiffness is decreased in these tendons, but for the Achilles, I think the meta-analysis has been demonstrating that we can assume that this is rather consistent in chronic cases. And that means that with our recommendations of rather high intensities of contractions, it may actually be that loading is unnecessarily high. We did one study with tendinopathy patients with Achilles tendinopathy. So our work in adolescent athletes were usually mixed, and severe cases of tendinopathy usually didn't take part in the experiments. But in this one study that addressed actually the patient population, and there we did not do personalized loading, but basically our generic recommendations with 90% of an NDC. And the reduction in pain was similar to, for example, the classic Alfredson eccentric loading and basically a physiotherapy group. But the loading program was the only one that was able to increase tendon mechanical properties. And the time spent in achieving these outcomes, particularly in regards or in comparison to Alfredson eccentric loading, which is suggested that we need to train twice every day, we have a way higher efficiency. So what does it mean? I think in terms of pain is basically even less or way less understood than tendon mechanical properties and how it responds to loading. I think it's, with regard to pain, you need to take personalized approaches. We also did so that if the heavy or high intensity loading was too painful for the participant, we needed to decrease the load. And I totally believe this is necessary. I'm not sure if there's already enough evidence to suggest that low intensity, long duration isometrics are more effective than, for example, high intensity, short duration isometrics. Not sure, maybe, but I don't know. Studies that show that. But for me, there is certainly a connection between mechanical, structural, and clinical aspects of tendinopathy, but how these aspects are connected is very individual and really hard to predict. So maybe one final word on that. So the inconsistencies we see in patient outcomes, both the clinical setting and particularly also research, I think a lot of this is also due to the fact that until now, or in almost every study, I would say, we actually do not know the degree of mechanical loading that was applied to the patients, to the tendon of the patients, because usually it's the the loading is defined with regard to one repetition maximum or the isometric maximum or something like that. So we focus on the muscle capacity, and to patients with the same exercise intensity, the actual strain on the tendon can be very different. And maybe there are some good results with regard to low or moderate loads because strain of the tendon was actually high. So this is still something I think these stories in the next 10 years may be also rewritten if in the experimental studies there is more control over the actual strain of tendons.
Yeah. Okay. Going back a little bit here, you said earlier on the tendon cell, the stimulus reducing with the high strain rates. So I'm thinking you don't see these gains in tendon stiffness, and that has to come from the tendon cell stimulus, right? So I'm thinking these high strain rate things. Are the cells just shielded from strain? Is that what you think's happening? Are they shielded from getting a pull on them, or is it that the cells need a little bit of time under tension of a pull to get this mechanotransduction? Because even going back to the whole anabolic catabolic thing, is if the high strain rates are like not getting this tendon cell stimulation, it would not be a catabolic thing for the tendon cell, or is it catabolic because you break down a bunch of collagen and then the cells can sense that? Yeah. If you can kind of piece together my question there.
Yeah. No, I can understand. It's an excellent question. And I wish I would have a good answer for that. But I could imagine basically if we or looking at this issue that climatic loading has very inhomogeneous responses. So this one thing is this viscoelastic property that may lead to a lower number of tenocytes receiving effective stimulation, and also, let's say, in homogeneous development of the mechanical micro damage that affects some fascicles maybe more than others at high loading rates, and that more homogeneous mechanical load to the tissue with a homogeneous stimulation of the tenocytes basically leads to a better possibility to also repair the wear of the tissue. Is that the right word, actually? Yeah.
Yeah, no, that actually makes a whole lot of sense. Yeah.
But unfortunately, this second point, which we argued, I think in some papers like that also, when there's high strain on the tissue, there are some mechanosensitive channels opening up at the tenocyte and cause, for example, influx of calcium. And until now, I do not know any study that modulated this. As I said, the in vitro studies usually do not have a period of constant strain that is maybe changed between protocols to actually see what happens, for example, on the cellular level. So this is just a speculation so far, and I would be greatly interested into getting this answer, but unfortunately, I don't have one.
Yeah, that does. I mean, it makes a lot of sense to me because patellar, I spent a lot of time with patellar tendinopathy, and it's the area of pathology is like usually the posterior kind of medial region that just gets overloaded time and time again. And it's like, if you're getting inhomogeneous strain on the tendon, maybe that's the location that you're getting it from the fast activities. And then the slow ones can kind of get maybe more well-developed tendon, a more thorough development of the whole tendon. I'm curious on this. When I was telling you before this Berlin method, I had seen it maybe it was a year ago, and I had never heard of it. And I was just like, it just seemed like it came out of nowhere. Because in the tendon world, you have like the Alfredson, the calf raises, you have like a 4-stage process, or you have longer isometric holds. How did you guys arrive at this? What is the exact thing? 4 sets of 3-second contractions done for 4 sets. with a 3 second. Yeah, can you kind of explain the set rep scheme? But how did this even come about?
Yeah. So basically, it started in Cologne when Professor Armbach was interested in systematically modulating these factors or strain magnitude, strain rate, strain duration, and strain frequency, and see the effect of the adaptation of tendon mechanical properties. And in his first study, they performed these 5 sets of 5 sets of 4 repetitions with 3-second contraction and 3-second rest. And they, in that study, they changed the loading magnitude. So 90% MVC, which corresponded in that participants to 4.5 to 5% strain, and 5% of the MVC, which corresponded to 2.5 to 3% strain, something like that. And they performed to achieve the same overall mechanical load. They performed a higher number of repetitions, but nevertheless, only the high magnitude loading caused a change in tendon stiffness. So in the next series of experiments, they used this protocol as a reference and reduced the contraction duration by factor 3. So they increased the number of repetitions by factor 3 as well to keep the overall loading volume constant. That was in the next study where they had this 1 repetition contraction duration, 1 repetition rest. And then here in Berlin, we addressed the issue of strain rate using plyometrics to obtain a very high strain rate as opposed to these isometric contractions which we had before. Also there, I think the factor was around 2.5 or something like that, so a 2.5 higher strain rate. And the contraction duration was modulated with regard to our reference protocol over 12 seconds. So basically, with all these different combinations, we were able to get a better image of how the single factors affect tendon adaptation and which factors are important, like, for example, strain magnitude, and which factors maybe not too important. And then at one point, we tried to condense basically all of this knowledge into a paper, like a handout material that can be given to practitioners. And since Arman Pautz is a modest guy and didn't want to put his name on it, he said, "Okay, let's call it the Berlin method." So that's the name, the reason why it's called Berlin method. But actually, it's just a collection of experimental findings from systematic research that address basically these 4 main components that determine the mechanical stimulus for tendons. So magnitude, rate, duration, and frequency.
Have you thought, so you guys have done it with patellar and Achilles. Have you thought if this could work for other tendons or not? Because these are the energy storage, quote unquote, tendons, the bigger ones that experience the big strains. Do you think other tendons would benefit? Would they even need this level of intensity?
The reason why we investigate the patella and Achilles tendon has methodological reasons. What we do, so measuring tendon stiffness in vivo, this to date can only be done with patella and Achilles tendon, because we not only need to measure accurately the deformation of the tendon in vivo, you also need to calculate tendon forces as good as possible, and there are a lot of limitations with the approaches that exist. And so currently, the most valid approach in vivo is Achilles and patella tendon. But basically, the overall composition and the mechanisms that translate the mechanical load into a cellular signal, they are similar in different tendons. There is, for example, with regard to the ultimate strain of tendon, there is a striking consistency across tendons and even across species. So we are very confident that our general recommendations, that they apply for all human tendons. With regard to the specific exercises that we basically suggest or that we give as inspiration for the practical field, usually, guys from the practical field, as you are way more creative and knowledgeable with regards to this exercise selection, which muscle tendon needs to load, in which conditions, which exercises, but basically the overall scheme of how to characterize the mechanical load. This is something that we want to provide, and we are confident that this works for other tendons as well. We receive some feedback, of course, from the practical field, for example, elbow tendinopathy or spinatus tendinopathy. And what we receive as feedback is very positive, that the approaches provide good outcomes. But we need to be clear here. There is not the miracle solution that works for everyone, particularly if we actually do not know a given load magnitude that we prescribe. How does the strain of the tendon, how high is the actual magnitude? This is particularly in patients still, a huge challenge.
Okay, we got a few minutes left before you got to go, but the thing we haven't talked too much about is the other thing. So you have the Berlin method and the stiffness of the tendon, mechanical strain. The other thing that I've kind of tried to understand, haven't understood too well, is the muscle-tendon imbalance thing. How did you guys come about with this idea that the muscle could be overdeveloped and the tendon is lagging, or the tendon is overdeveloped and the muscle is lagging? How did you guys arrive at this?
That is basically based on the findings of this first experimental study that Aaron Patzels has been doing alone on tendon adaptation, where this high magnitude, high strain loading and low strain loading was compared, because in the protocol with the lower strain magnitude, which was corresponding to 55% of an isometric MVC, these participants, they didn't have a change in tendon stiffness, but they had a change in muscle strength. And that basically the result was that during a maximum effort muscle contraction, the strain of the tendon was higher. And at about the same time, there have been some reports, first in rats and then in humans as well, from the group of Montpellier. They go a lot into the physiology of tendon adaptation, in which factors are involved with that. And they also had some indications that a high number of loading cycles, fatiguing contractions with rather moderate load, that the expression factors for muscle adaptation demonstrate a stronger response than those for tendon. And they also started to speculate that it could be possible that certain types of loading could be more effective for the muscle as opposed to tendon. And that is basically how this idea came across. And in my PhD, for example, we were looking specifically into adolescent athletes in a large-scale longitudinal study where we had 5 measurement time points over 1 year, measuring the same participants multiple times and also a control group. And we're actually observing exactly that we had rather high fluctuations both in muscle strength and in tendon stiffness in the athletes as compared to controls. So let's say, physical activity or sport activity on an elite level is a strong disturbance, let's say, of the tissue homeostasis of both muscle and tendon, and that this adaptation in a lot of cases does not go in line. So, you can have increases in strength at rather constant levels of tendon stiffness. And sometimes we even observed changes in tendon stiffness without increases in tendon strength. There's a lot of things we do not know for the reasons that are associated. But I mean, we have now much more evidence demonstrating that particular modes of loading have the potential to change, for example, muscle strength, muscle capacity more than tendon stiffness. And we also have some evidence from the group by Kyros Karamanidis, for example, who was until recently in London, did a lot of work there. For example, they've been training, I think, in one protocol even 3 times a day. And it was very soon that they observed a reduction in tendon stiffness. So while when we come back to our earlier point in the discussion, during one acute bout of loading, usually the muscle would fatigue earlier than the tendon. But if you give the muscle some rest to recover, and you train over several days, multiple times a day, then you reach a point where the tendon seems to be mechanically worn off, or there's an accumulation of micro damage in the tendon which cannot be compensated for by its metabolism. And then this leads, for example, to a decrease in tendon stiffness, and maybe potentially also overload in the long or midterm. So yeah, I think it's aside from this individual predisposition, which could lead to a less sensitive tendon with regard to adaptation. I think particularly load management is something which is in general very important, and in some athletes or some people in particular. Also coming back to tendinopathy, right? This Alfredson loading protocol. In my view, the mechanical loading provided with this protocol is way too much. Still, it has good outcomes in terms of pain in a lot of cases, but in terms of tendon structure and tendon mechanical properties, the outcomes are not so convincing.
Yeah. What do you see? I said at 1 hour. You have 1 hour, so I got a couple minutes. The deficit. You said the deficit in muscle strength is rare earlier. You mostly see a deficit in tendon stiffness, right? Yeah. So what would be your suggestion for people? If people listening, they probably have maybe not probably, but it's more likely that they would have a deficit in tendon stiffness. What is your suggestion for the loading? Like the Berlin method is one way to increase it. The loading, the rest periods, what would you suggest?
So in general, also not to be misunderstood, because I've been mentioning a lot of times that plyometric loading is not as effective on tendon adaptation, and that athletes which are subjected to a high volume of plyometric loading, they in many cases develop overuse injury. A lot of athletes, when we do workshops and so on, are asking, are we not allowed to do plyometrics anymore? And I just want to say, of course you are, and of course it's extremely important for sports performance to use plyometrics, because it's very well capable of improving neuromuscular function, and particularly the muscle-tendon interaction aspect, which we did not discuss much about now. But for performance, that is really the precise neural control of this interplay is extremely important. So definitely you can do that. But my suggestion is, for almost everyone who does not know if there is a, for example, muscle tendon imbalance. Currently, we do not have no widely available method to determine if that is the case. We have a lot of studies where we applied specific tendon training to the group of athletes without personalized load prescription and also without identifying any deficits beforehand. So just we integrated as part of their routine about 15 minutes, 3 times a week. At the beginning of their exercise session, so after the general warm-up, they did both isometric and also some dynamic exercises, which were loading the tendon rather high, so rather high loads, rather slowly applied, held for certain duration, 3 to 6 seconds per execution, and the overall loading volume of this was rather small. And in general, we had very positive outcomes. We had a lower rate of athletes that developed overuse symptoms from athletes which already had mild symptoms. We had a higher rate of improvements. Also on the structural side, we saw that athletes which had rather high strains, that they did not show structural changes of the tendons, which are sometimes already an indication of structural deterioration. So the outcomes were in general very positive, and the time investment was quite low. So particularly, if you're ambitious, if you train maybe more than or 3 or more sessions per week in jump intensive sports like basketball, volleyball, or in general the game sports and jump discipline from track and field, my strong suggestion would be to implement this on a regular basis, maybe 3 times a week, 3 to 5 sets with 4 repetitions of moderate duration, 3 to 6 seconds contraction duration, rather high loads. These are the general recommendations.
Yeah. Okay. I don't want to take any more of your time. This was good. I probably have 20 more questions for you, but we'll have to do it another time. Tell people where to find you online. I know you're not in too many places, but yeah.
Yeah, actually, we have not really a social media presence, but maybe you can post the link to our department homepage under this in the description of this podcast, and also my email address. And I'm glad to answer all the questions. When just write an email and we'll receive a response.
Okay, yeah, I'll do that. You also had a few studies. I'm going to email you to get those studies you were talking about, because I've never seen those before. But all right, Falk, thanks for coming on. This has answered a lot of my own questions, and now I'm questioning a lot of things as well. But yeah, thank you for coming on.
Thank you very much. It was a pleasure. It's always good if some questions are answered and new ones are coming up. That's the same. This is my daily business. When I'm able to answer 2 questions, I have 3 more myself. So
yeah, exactly. All right, thank you.